Hello again, friends. Welcome to this lecture, the next lecture on in the series Cosmological Perturbation Theory. Today we will look at perturbations in the Fourier space. Uh, Now, every perturbation can be expanded in the Fourier space as like this. And why we want to look at perturbations in the Fourier space? First thing is that we are looking at linear perturbations. We are dropping the terms, we are keeping only the terms up to first order and dropping all the higher order perturbations. And because of this linear nature of perturbations, when we plug in when we replace the perturbation term with this Fourier expansion term in the equations, we will see that in the equations you can let me just explain it in writing. For example, I have any random equation. A square b plus c square d is equal to e cube. This is any random equation. And I am writing this as a plus delta a, this as b plus delta b square. Now, what does this term simplify to? This will become a square plus 2 times delta a. I will ignore the higher order term. This will become, this is this b plus delta b, b plus delta b. So I will have a square b, this is bar here, a square b plus 2 times delta a b bar plus, is there anything else? 2 times plus a square this a square delta b. Now I am ignoring this also. So this is the expression for a square b. Similarly, you will have expressions for c square d and e cube. Now, if you see that in this expression, this is the perturbation in a square b. Let's call it a perturbation in a square b. Perturbation in a square b. So if you look at the perturbation in a square b, and because we are keeping only the linear terms, dropping the higher order terms, what does perturbation, I will call it PERT, perturbation in a square b, what does this look like? This is this. Okay. Now I write this in terms of its Fourier components. If I plug in the Fourier components, it will be delta a k Fourier coefficient eta, which is a function of eta, and e to the power k. So when you are writing Fourier expansion, then you can see that the spatial part is in this exponential part. So the spatial part goes to exponential, the spatial contribution goes to exponential, and you are left with the eta contribution, which comes in the Fourier coefficient term. So this Fourier coefficient fk is a function of eta only, because the spatial part now goes to this exponential term e to the power I k dot x. So that takes care of the spatial part, and this fk eta contains the contribution, this Fourier coefficient as a function of conformal time eta. So I have this delta ak eta and plus a square Fourier expansion of delta b. Fourier expansion of delta b is delta bk eta e to the power I kx, and I can write this as 2 times sum over all Fourier coefficients. There is b bar here. 2 times b bar sum over delta ak plus a bar square sum over all k delta bk e to the power kx. In other words, I can write this as sum over all k 2 b bar delta ak plus a bar square delta bk to the power iota kx. Now you see that this equation is exactly same as the original perturbation equation without the Fourier coefficients in the Euclidean space. So this is the original perturbation equation in the Euclidean space, and this is now we have the perturbation equation in the Fourier space. So because of the linear nature of perturbations, I am just replacing the perturbation value with its Fourier coefficient, and then of course I have this e to the power iota kx and this summation sign. But what is this 2b bar delta ak? It is coming from this term, and this a square delta bk is coming from this term. All I am doing is that I am, like, after doing all this manipulation, mathematics equation manipulations, I am this Fourier coefficient comes from this original expression by just replacing delta a with delta k, delta ak, and delta b with delta bk. So because of this, it is very helpful. Now I can it is very helpful to write the perturbations in terms of Fourier coefficients. I have one Fourier coefficient function of eta. So I am expressing, because of the linear nature of perturbations, I am able to express perturbations in terms of its Fourier coefficients, which is 2b bar for this particular example plus a square delta b. That expression which the original expression, perturbation expression, was delta f, you can say. Delta f becomes this. So the original perturbation expression, which was 2b bar delta a plus a square delta b, can be expressed in terms of its Fourier coefficient, and the Fourier coefficient is just you are replacing the perturbation with its perturbations Fourier coefficient. So any equation you can, if you have a equation containing perturbation, any equation that contains perturbation, any equation that contains perturbation, just replace that perturbation, which the perturbation in four-dimensional space-time. You just replace the perturbation with its Fourier coefficient. Replace with its Fourier coefficient. Fourier coefficient as a function of eta. Perturbation is a function of, this is a function of x alpha, and you replace it with its Fourier coefficient, which is a function of eta, and then just keep the whole equation as it is, and just replace, keep the terms as it is, just replace the terms with the Fourier coefficient. So each term, so the equation for each k mode, we call it k mode, for each Fourier mode, we are able to express the, for each k mode, the perturbation equation is valid. For each k mode, this perturbation equation is valid. This or any perturbation equation. This is just an example, but it like we will apply this perturbation to when we are doing like say connection coefficients, Ricci tensor, Einstein equation. Then we will apply all this machinery Fourier space mathematical formulation which we are building right now, and we will apply this to solve those equations, and we will see that all we are doing is we are just replacing the original term which is in four-dimensional space-time with the k mode perturbation term. So that's it. So keep the equation same, and any k, like for any arbitrary k mode, just replace it with just replace the perturbation, original perturbation. Like we have original expression was 2b bar delta a plus a square delta b. Just replace it with delta a k delta b k. That's it. And then the whole equation will remain as it is. Just replace with Fourier coefficients. Now, yes. Another thing as a part of making the notation easier, to make notation easier, and this we will apply when we are going to solve equations. To make notation easier, what we are going to do is to make the notation easier. We are going to drop these sub-coefficients k vector k. So write delta a k simply as delta a, delta b k simply as delta b. Now when you drop these subscripts k, it may look like original perturbation in the four-dimensional space-time. You may, but then we have to keep it in mind that we are in Fourier space. So when after we drop k vector and write the equation in terms of k modes, perturbations in k modes, each perturbation delta a, delta b is in k mode, we will drop the k's because it is implied, this k space, Fourier space is implied that now we are in Fourier space. So we don't have to write k vector all the time. So this is just to make the notation to simplify the notation. So from the context, once we open the door for the Fourier dimension, then we don't have to carry this k vector in our we don't need to put this label that we are in the Fourier space. We will just remember that we are in the Fourier space. So we will do all the calculations. We will like in the Fourier space, and if we have to go back to four-dimensional space-time, then once again we will close the door of the Fourier space and we will open the door of the four-dimensional space-time, and then we will remember that we are in four-dimensional space-time. So when you open the door of Fourier space, remember that you are in Fourier space. No need to put this vector k. Just remember that you are in the Fourier space. Okay. Now let's see what else we can do in the Fourier dimension, in the Fourier space, before we look at the application of all this Fourier expansion application to the application in the cosmological perturbation theory. Okay, let's review this basic terminology which you have seen in other courses as well. So what is this fk? You are expanding this any function f. F is any function. In our case, this will be perturbation, but this can be any function. This can be scalar, vector, or tensor, or any perturbation, or any function. You can write this as expansion of Fourier series like this. And what is this? This is a wave, because Fourier expansion is a superposition of waves. Each of this term is a wave. What is x? X is co-moving vector. I don't know if it is visible enough in the video, or should I enlarge the font size? Won't let me increase the font size. I have increased the font size to improve the readability. So each of this term fk eta e to the power I k dot x is a wave. X is a co-moving space vector. K is a co-moving wave vector. K is a co-moving wave vector. X is a co-moving space vector. Fk is the Fourier amplitude, and for the wave vector or k mode, or wave, you can say wave vector k. Fk is the Fourier amplitude, and it is a function of conformal time, because the spatial dependency is moved to this part now, and this is only function of conformal space-time. Now the wave number, the co-moving wave number is k. The co-moving wavelength is lambda 2 pi over k. The physical wavelength is the co-moving wavelength multiplied by the scale factor, so it is 2 pi a over k. So the physical wavelength grows as a universe expands, but the co-moving wavelength remains the same. The physical wave number k physical is equal to 2 pi over lambda physical. 2 pi lambda physical is a lambda. 2 pi over a lambda is equal to k over a, and this k is the co-moving wave vector. So the physical value of k will decrease as the universe expands. So as the universe expands, lambda will increase, physical wavelength will increase, and k will decrease for a given co-moving wave vector k. Now let us look at how this would some important relationships using the index notation. And again, the font is not clear here, but anyway, I'm going to explain this in writing. Let's the note. So we would like to see how Fi looks in the index notation. What is Fi? Fi is basically this thing, or you can say basically del F by partial differentiation with respect to xi. How does it look in the index notation? Index notation in K space. So we would like to see the index notation in K space. K space means Fourier space. So index notation in Fourier space. So how would this look like in Fourier space? If I have any function f, which is a function of x alpha, I can write this as f k vector eta e I k dot x. Now when I take partial derivative with respect to xi, what will I get? Now what is this? This is k1 x1 plus k2 x2 plus k3 x3, right? So if I am taking derivative with respect to x1, k1 will come front. If I am taking derivative with respect to x2, k2 will come on in front. Taking derivative with respect to x3, k3 will come in front. So if I'm taking derivative with respect to I, ki will come in front. Iota, there is I here also. So iota also will come. Do not confuse this iota with this I. So this is iota and this is index. This is not index. Not index. This is iota. And this is index. Okay, so we have fk. What else? Rest everything is the same. K dot x. So now if I were to express Fourier mode of this, what is the, let's fi, right? So what is the Fourier coefficient of this? What is the Fourier coefficient of this? This is a vector. This is a vector. Basically, this is del f, a vector. So I am expressing del f in the Fourier space using index notation. So this is what I am doing. This is del f. So I am expressing del f in Fourier space, in K space, using index notation. So how is del f written in K space using index notation? Uh, it will be, which means I want to know its Fourier coefficient. This. So in perturbation, whenever you have to replace del f, in equations, in expressions, whenever you have to replace del f with its perturbation value, just replace del f with this. So del f becomes, this is in x space, and in K space this will become, and remember I told you that we can drop the subscript. So in K space this will become this, in K space. So del f becomes this in K space. What is the next thing we want to look at? We want to look at gradient. Sorry, gradient we have seen. Next we want to look at del square. So if you have del square f, then what do you do? So f is, del square f means you are going to do this, del square f, del square of fk eik dot x. Sorry, should I say x here, or maybe, yeah, so yeah, x, that's fine. So how do I, basically x means that x1 x2 x3, x1 x2 x3. Now how do I write this in the Fourier space using index notation? So when I do first derivative, I get iota k I. So what I am interested in is that I component of this. Yeah, so this is, sorry, there is no I component here. So this is del square. Del square will be equal to, we can write this as this is equal to del square f is equal to del square by del x1 square plus del square by del x2 square plus del this by del x3 square. This. So when I do this, apply this derivative, double derivative here, I will get square k1 square plus iota square k2 square plus iota square k 3 square, and this is equal to minus k1 square plus k2 square plus k3 square. It is the magnitude of k square. So this is what in index notation, sorry, in k space, there is no index here. In k space, you can replace delta square f with minus k square f. There was a sigma sign here. Sum over k, sum over k, sum over k, and sum over k. Yeah, so minus k is, and yeah, and this will continue here. This will continue here. E to the power I k dot x. To the power I k dot x. Yeah. But when you are expressing in the k space, the Fourier coefficient is this. So this in the x space will be replaced by this in the k space. Now let us see how the metric perturbation components they expand in the Fourier space. We have seen that we have the following components: A, B, G, E, scalars, BV vector BV, and or you, if you want to write in index notation, then BVI and BVI and EI vectors, and tensor ETIJ tensor. How can you write them in the Fourier space? Let us see how we can write scalars in the Fourier space. You have a scalar A. You can write this as AK, like this. And A is a function of x alpha. This is a function of x alpha, and this is a function of eta. So A in x space will be replaced with AK in Fourier space, and we will drop the subscript k. So this is x space and this is Fourier space. A will become A, and after dropping the subscript k, you can say it will become A. So simply replace A with A, and same would apply to D as well. Simply you replace D with dk. In the equations, replace D with dk, and if you we don't need the subscript k, so simply replace D with D. Now how about, so that applies to A and D. Next we want to see that how about B, which is extracted from BI. So remember that we wrote BI as curl free component, scalar component, which gives us which is curl free, and divergence free, BVI. This gave us minus this, and this gives us this scalar B. So B is a scalar extracted from BI. How will we express B in which is in X space? How we will express it in K space? So how to express B in K space? So we will not simply write it like this, the way we have written. We will follow a slightly different approach for writing the value of this B in K space. And the reason for that is because you see that this B and this B, they are dimensionally different quantities. For example, if you have this B is voltage and this is electric field, for example, which you have seen in electrodynamics. So those two are different. One is scalar and having different units. And this, if this is electric, this is voltage, this is electric field. They are, one is scalar, one is vector. They both have different units. So, but what we want is, we want to see in our expressions same unit. We want to see the unit of B same as that of BI. So that would give us when we look at equations, so we want to see as if when we are looking at B, we want to see that we are looking at BI. But right now, if you see that they are not the same because dimensionally they are different. Let us see how we can express this B in K space, how we expand B in K space. Let us first of all write the Fourier expansion of vector B. So I can write vector B, or let me write a general vector. Instead of saying vector B, I can write any general vector, say W. W, which is a function of x alpha. I can write this as W k, which is a function of eta, and e to the power I k x, like this. So this is a Fourier expansion of a vector W. Now, what is vector W? This is basically a scalar plus vector part. I mean, this is a curl free part, and this is divergence free part, which we have seen in the previous videos, is equal to WK EIKX. Now I can expand this in Fourier space as WS K EIKX, and this expands as WV EIKX. So when I combine these two, I can see that WS K plus WVK IKX W K EIKX. So I can clearly see that wk is equal to wk scalar plus wk vector. Now, what is W scalar? W scalar is equal to minus gradient of W. W is the potential, scalar potential, the scalar which we extracted from the original W. So remember, the original W is this. From this original W, we split it into scalar and vector parts, and from scalar part we extracted the potential W. So this is W. It is not the magnitude of the original vector, but it is the scalar potential of the original vector in this context. So this is Ws is minus W, and if I can write W as BKEIKX. Now, why BK? Why not WK? There is a reason why I am not writing WK. Because I told you that our expansion will be different from the expansion which we have done for the other scalars. So the ones which we are deriving from vectors and tensors, we are taking slightly different route. So I'm not going to call it WK, because then I'm following the same method which I have followed for other scalar. Here I'm going to take a slightly different route. So temporarily I'm going to call it BK, but we will come to WK. Let's see that if I write it like this, then what do I get for this W scalar? For W scalar, I would get for W scalar vector, I need to take a gradient of this. After taking gradient of this, I would get and we have negative sign here. So this is what we get. So when we take gradient of this. So this is W scalar. And now see that if since this is equal to WK scalar EIKX, therefore WK scalar is minus IBKK. Now note that BK is not BK and WK, they have different dimensions. So BK and WK as or the original WK or original WS, original W, they have different dimensions. So yeah, so you see that we started with W is equal to this. So this W and this WS, they have same dimension, and WS and WSK, this also has same dimensions. So this and this, they have same dimensions. But here what we are getting is after taking the gradient of the potential W, the coefficient which we are getting for WS, which is minus I BK, BK and the original W vector, they have the different units or dimensions. So they have different units. Where is BK? Yeah, and BK has same units as W. It has same units as W, same units as W, but different units as W, as the vector W. It has same units as the potential W, but different units as the original vector W. And that makes sense because this W, gradient of this W has the same units as this W. So this having different units makes sense. Now, but what we want is that when we look at the perturbation, we want to look at as if we are looking at this vector, but its scalar part. So which means I want to keep this component dimension same as this. So I'm replacing vector with a scalar, but I want to keep the dimension same. So if I want to keep the dimension same, that means when I write this as W yeah. So when I yeah. So what is BK? BK is the coefficient of the expansion, the Fourier expansion of scalar potential. So scalar potential is expanded in terms of BK like this. Now, if from here onwards, there are two conventions which you will find in the textbooks. Convention 1. Convention 1. Convention 1 is that you replace BK with, let me see, BK with I, BK with I, WK over K. So when you do this replacement of BK with the I, WK over K, then you see that the scalar WKS becomes, we put instead of BK, we put this. So this will become, sorry, this is WK. This will become WK over K. It's K vector. And note that this wk scalar, note that wk scalar is parallel to k. So we are splitting this wk into two parts. What is wk vector? wk vector is the Fourier coefficient of the original w vector. So we have we write the original w vector in terms of the Fourier coefficient wk. Then we split wk into two parts, wks and wkv. And when we do the write this w, what is this? Yeah. So when we write this w in terms of its Fourier series, when we write the Fourier series of w, take its gradient, and after taking gradient, when we look at its Fourier coefficient, we see that the Fourier coefficient of the scalar this vector, this curl free vector, its Fourier coefficient is parallel to k. So that's what we see, that this wks is parallel to k. And now I want to express this in terms of wk, not bk. So when I want to express this in terms of wk, not in terms of bk, and also I want to make the units of wk same as the units of the original w, or you can say this wks vector. So what I will do is that by convention 1 is to put bk in terms of wk like this. So when I do that, I get wks like this. So now you see that wks and wk, they have the same units. And what is the potential w? Fourier expansion of the potential w. Its Fourier expansion will now be, instead of bk, I have this. So this is unit vector k. So I think this iota should not be there. I have bk, iota and iota square will be -1. So I have this and this multiply -1 and minus. So this should be, this iota should not be there. This. So you see that in convention 1 we have a potential given by this relationship, and this is what we will use when we have to replace the potential with the value in the k space. And 1 second, there is something not right, because on the left hand side we have a scalar. No, this is something is not right here, because on the right hand side this is a vector, and yeah, so this is wks. Okay, so 1 second, let me rewrite this. I will rewrite this. Let me rewrite this. Let's rewrite this. So I got the value in convention 1 for wks. And what is wks? sorry, what is vector WS? Vector WS is Fourier expansion of this is a coefficient WKS vector, which will now be replaced with WK over K E iota KX and over K. Yeah. And what is W? This is the expansion of WS. And what is the expansion of yeah, so is this right? Looks right, I think. Yeah. What is the expansion of W? Expansion of W is sum over K, and BK is replaced with this, so we have IWK over K IKX. So this is convention 1. WS is given by this and W is given by this. Now let us see what is convention 2. In convention 2, we would not like to keep this iota sign here. We would like to express W. In convention 2, we would like to express W without iota, like to express W like this. Want to express W like this. How can we express W like this? So I can write BK as WK over K. So I will write BK without iota. So in this case, I would write BK as WK over K, and then W becomes this. And what is W scalar? Expansion of W scalar becomes that becomes like for its Fourier coefficient becomes minus I BK, which is this. So WK W S expands according to this expansion minus the WK over K and potential expands according to this. So the only difference here is if you compare the potentials of convention 1 and convention 2, the only difference is that of the phase. Here we have iota and here we don't have iota. And similarly, if you look at the expansion of the scalar WS, here we don't have iota in convention 1. In convention 2, we have minus iota. So there is only difference of phase in the Fourier coefficients, and Fourier coefficients are complex terms. So by taking a phase out, like iota out, you are not changing the magnitude of the Fourier coefficient. In both cases, the magnitude is the same, and it's only a difference of phase. So we will follow this convention 2. Convention 1 is followed by Doddelson in his textbook. Convention 2 is followed by Liddell and Lith textbook, and also by the Helsinki uh, course on cosmological perturbation, which is published online on their website. They are also following this convention too. So I would also follow the convention too, and any scalar which is derived from a vector will be expanded using this convention. So, I think I made a mistake here. The mistake is that this is without vector at the bottom. This is k, not vector k. Okay, so I will expand what are the perturbations that we derived from a vector. That perturbation which we derived from vector was b. We extracted potential b from vector bi. Bi gave us potential b and vector bvi. So on b, on the Fourier expansion of b, I will apply this rule. I will expand b according to this rule. So I will say that b is equal to bk over k e I kx. So this is b in x space, and this is Fourier potential in the k space. So in k space, I will have bk and here b. So the relationship between them is according to this expansion. Okay, now let us look at so we have seen the expansion of B. Now we need to see how are we going to expand the the scalar and yeah, so how are we going to expand the scalars and vectors extracted from EIJ tensor. So from EIJ tensor, we extracted a scalar E and we extracted a vector EI. How are we going to do Fourier expansion of these two? Fourier expansion of EI will be done like this. And this is again just a convention. And why are we doing it like this? So that the k Fourier coefficient and EIJ have same dimensions. So what is EIJ basically, or you can say EIJ Ej's dimension is same as that of Eij vector, from which we extracted this vector Eik. So this is vector Ei. Yeah, from which we extracted vector Ei. We extracted vector Ei from Eijv, and Eijv and Eij, they have same dimensions. So the components of Eijv and the components of this Ei, we want them to have same dimension. I mean this Ei in Fourier space. Fourier space. So we want them to have same dimensions. So what is Eijv? It is half Eij plus Eji. That means this is obtained by taking derivative so by taking derivative of Ei, we will get same dimension as Eijv. So when I divide by k and I take a derivative of this, if I take derivative of this, then when I take derivative of this Eij, then iota k comes in front. So Eij will be Eik and this. So you see that Eij and Eik, they have the same dimensions, and that is what we want. So we want them to have the same dimensions. That is why we divide by factor of k. Now let us see how we can do the same for scalar. How is scalar achieved? Scalar is achieved by differentiating scalar E, when differentiating twice, it has the same dimension as Eij. So that means I need to differentiate E twice to get same dimension as Eij. So let me write this scalar E as, and if you are not sure like what factor we should bring, k square, then you can first write it like this, and then you differentiate this twice. When you differentiate this twice, like let us say I differentiate this twice, I will get iota square minus 1. Ki, kj, yeah. So you see that this has dimension of b, k and k square. So I want this term to have dimension of Eij. So what I can do is that if I want to write this in terms of yeah. So this is having dimensions of Eij, and I want E to have the same dimensions as the dimensions of Eij. So I want E to have, I want, if I can write the Fourier expansion of E like this, that means I'm going to replace bk with ek by k square, so that ek has the same dimension as Eij. Because if you write bk like this, now ek will have same dimension as Eij, because bk k square is equivalent to ek and bk k square is equivalent to Eij, and I can write this as E is equal to ek over k square ei kx sum over k. That's how I would expand the scalar which is derived from a tensor. Yes. And vector which is derived from a tensor, I will expand like this. Again, the whole idea is that I want to keep the unit of the coefficient same as that of the original perturbation, which is tensor in this case. So I want this coefficient to be same as units of this Eik to be same as that of the terms inside Eij. That is why I'm dividing here by k and here by k square. Okay, thank you guys. See you next time.